Hey, Natalie, can you hear me?
Hi, Scott. Yes, I can.
Okay, great. Just wanted to make sure. Natalie, is Massimo online?
Yes, he is.
Okay.
Yes, I am.
All right, great. Thanks. I just wanted to make sure before I start introducing you. So it is now 12 o'clock my time here in Los Angeles. So I'll start the introduction for our webinar today. Before I introduce Massimo, I'm going to give a brief overview of DesignSafe and then hand it over to him to present the scientific toolkit for OpenSees, STKO. Come here. There we go. So the DesignSafe-CI vision is that it's a cyber infrastructure that's an integral and dynamic part of research discovery. So it's not just designed to be a file repository, it's part of our research workflow. And it has cloud-based tools that support analysis, visualization, integration of diverse data types, supports end-to-end research workflows and the full research lifecycle, and really enhances and amplifies the capabilities of the other NHERI components. I should mention that I'm doing the introduction today because Charlie Day had a conference to attend. So you're stuck with me doing the introduction here. I'm part of the DesignSafe data requirements team and have used it quite a bit. So I'm a big fan of the capabilities here. This is a schematic of the DesignSafe workflow. So on the top, we have simulation research, which is what Massimo will talk about today, and in particular, visualizing OpenSees results. Then, of course, there's experimental research and rapid reconnaissance research. And that information all gets stored in the data depot, which is a file system that allows users to put their information in. And importantly, there's also the discovery workspace. So that's a collection of tools that users can use to interact with their data. Data analysis and visualization, there's simulation tools, and of course, output from those tools can also be stored in the data depot. And importantly, users can curate and publish their data through DesignSafe. So it's not just going to kind of be there as a file repository. You can publish it, it will persist forever, and you can cite it. So getting your data into DesignSafe can sometimes be a little bit of a challenge. So I just wanted to go over some of the options available. If you have a small number of small files, you can upload directly using the data depot or using a Python script in a Jupyter notebook. If you try and use those tools for a large number of files or very large file sizes, it may not work. So if you happen to have those files in Box, Dropbox, or Google Drive, it's really easy to get data back and forth between Box, Google Drive, Dropbox, and DesignSafe. Works really well. If you have a large number of large files locally on your own computer, Globus is a good option. It takes a little bit of effort to set up, but once it's set up, it basically works like a kind of a web-based client where you can just drag files back and forth. And I've used all of these options and they're all pretty straightforward. Then there's also command line interface commands that can be used, rsync and scp and so forth. Once the data is in there, our philosophy is that we want to make it easy for users to store their data, share it with members of their project team, document the data, and ultimately publish it. And we want it to be done throughout the life of the project. So DesignSafe is not envisioned as a file repository where you do all of your work and then you go put it in DesignSafe to make it publicly available to meet the NSF requirement that your data be published or something like that. Our intention is really to provide something that's useful throughout the life of the project. And we have a number of different data models that are flexible, and you can organize your data using these models. And the models that we have are for experimental simulation, hybrid simulation, which is kind of a mix of numerical and experimental. And there's a field reconnaissance data model and a social science one, and then an other data model, which is kind of a catch-all that is a little bit more free-form. And if you work in a research community that is not well covered by the existing data models, let us know. We'll work with you to develop one. And if you have any questions about these data models or curating or publishing your data, there is also office hours with Dr. Maria Esteva, who's the data curator for DesignSafe, and she holds Zoom office hours. You can log in and learn more about data publishing. Then in DesignSafe, you first define, when you go to curate and publish your data, you first define a category tree. So this is like all of the buckets that you'd want to put your data into. So here we're showing model configuration, sensor information, and events. And once you've set up that kind of organizational structure, you go into the data depot and assign categories to the files that you would like to publish. Generally, a project will consist of a large number of files, and only some of them are files that you'd want to publish. So there's no requirement to publish everything. You can go in and select which files to publish by categorizing them with the entities that you've defined in the category tree. Then once you've done that, you can go through the publication pipeline. This will show you a view of what the data will look like for external users when they come to DesignSafe to look at your data. And then when you finally push the publish button, your data will be assigned a digital object identifier, or DOI. And a DOI is not just a URL that points to DesignSafe. It's an identifier that is required to persist forever. So if you go to the website doi.org/ and then put in the DOI number, it will always point to the right place because DesignSafe has agreed to make sure that that happens. Okay, and then once you have a DOI, the nice thing is you can formally cite your data in your reference list. So if you write a paper that uses some experimental data, whether it's your own data or somebody else's data, instead of just putting in the text that you got the data from DesignSafe or something like that, you can put a citation in the references section of the paper, and then everybody will know exactly what you're talking about, and they'll know exactly where to find it. So here's an example of a DOI citation from a paper that was co-authored by Ellen Rathje and published in DesignSafe. So now I will turn it over to Massimo Petracca to talk about STKO, which is a scientific toolkit for OpenSees. It's been developed by AsdeaSoft, and it's a powerful pre- and post-processor to develop simulations and visualize their results. So users can create tool command language or TICL input files for OpenSees, and then the output file is readable by the STKO graphical interface. And you can then customize and manipulate with a Python-based scripting interface the model input and output to create customized engineering demand parameters and output data. So let's see, I'm going to go ahead and stop sharing, and then Massimo, you can take over the share.
Here I am. Can you hear me?
Yeah, I can hear you.
Okay, so thank you for the introduction. Let me share my screen. Okay, do you see the screen?
Yes.
Okay, so I will first start with a very brief introduction about STKO for those of you who are new to STKO, just 10 minutes. And then the idea is to start with a simple tutorial on how to use STKO through DesignSafe, starting from the preprocessing up to creating the model file and TICL input files. And then we'll run OpenSees MP. So we'll do a test on a parallel version of OpenSees. And then we will see the results on the postprocessor. So let me first start with talking a little bit about STKO. Here is the outline. I will talk about STKO. We'll talk a little bit about the motivations that led us to the creation of this user interface. And then I will give you this quick tutorial. Well, the tutorial will be very easy because this is the first one, so I will not focus on complex models. I will do a very simple model, and the main aim here is to explain you the entire workflow. Okay, so why do we need a new tool like STKO? Well, because when we try to analyze real-life structures, this often leads to very complex models, and writing TCOL files by hand is not so easy. So we need a GUI, but we don't need the typical black box that we have around for proprietary softwares. We want something which is open, so we call it an open box, through a scripting interface. And then, of course, we have a lot of issues also for post-processing, because when we analyze real-life structures, we have large size of data, we have heterogeneous results, and we want to visualize them all at once. And very often we have a lack of visualization tools for particular outputs, such as those defined on fibers. And these are the main reasons why we decided to create STKO. So, of course, STKO is a pre- and post-processor. So this is a brief overview of the preprocessor. You can start with a CAD modeling, so you can do your own curved surface or solid modeler. Then you can go to the interactions. Basically, interactions are tools used to connect these joint geometries. Like, for example, if you want to create contact pairs or kinematic constraints. Then there is all this section about assigning material properties, sections, and finite element formulation. So all the physics of the problem are set up here. And then you move to boundary conditions and you define all the analysis steps, so you're ready to run the analysis. Then, of course, we have the meshing tools. The meshing is just the last step before running the analysis. We have all kind of meshing algorithms that we need. And then we have this nice feature. Basically, as you know, OpenSees, for OpenSees, we have three kinds of versions of OpenSees: the sequential one and two that are parallel, the OpenSees SP and OpenSees NP. Now, typically, people use OpenSees SP to run large models, while OpenSees NP is used to run parametric studies. But actually, they do so just because writing TCOL files for OpenSees NP, I mean, for a single large model, is not so easy because you need to have those TCOL files already partitioned. And this is not so easy to do by hand. So we decided in STKO to offer this possibility. So when you do the mesh, basically you can do your own partition. So you can decide how many partitions you want. STKO will then write the TCOL file for the OpenSees NP. So you can just run them. So you eliminate the overhead of OpenSees SP, because with OpenSees SP, you first have to create the entire model on a single processor, and then it will partition the model. While with OpenSees SP is already partitioned. And then you just write the TCOL file and run the analysis. Now let's move to the postprocessor. Well, the postprocessor has all these standard outputs that we will see later, so surface plots, volume plots, and then we have some new features that we wanted and we couldn't find in other postprocessor, which is the visualization of fibers. And then the first thing that I want to mention is that OpenSees is not integrated inside STKO. STKO is just a pre- and post-processor, so you need to have OpenSees on your own system or on DesignSafe. And what OpenSees version do we need? Well, basically, you can use both the sequential and the two parallel version. It doesn't matter, but the version of OpenSees should be equal to or higher than version 3. Why? Because we need the NPCO recorder command. Basically, the NPCO recorder is a new recorder that we implemented in OpenSees and allows us to write the so-called HDF5 database. And these are a few reasons why we decided not to use the text-based recorders already available in OpenSees. We decided to go with a more general database. Why? Because we not only need the results as the text files that are already available in OpenSees. We need a lot of other information if we want to build a GUI. So we need, for example, the entire model, the nodes, the elements, the cross-section that have been assigned to those elements, for example, the fibers, all the Gauss integration rules. So all this stuff that basically allows us to create this kind of visualizations. And then another nice thing that we have in STKO is the scripting interface. Now, basically, the entire connection between STKO and OpenSees is done in Python. So it's not hard-coded inside the C++ code of STKO, but it's in Python, so the user can see it, they can modify it, and they can actually even customize it. So, for example, in this case, we have an example of a researcher that decided to implement material calibration, automatic calibration material parameters, which is very useful, for example, when some material models are very difficult to calibrate, so you can just input the experimental results, and then through a genetic algorithm, you will try to calibrate material models. And this one is another example of an automatic calculation of the properties for the confined concrete, starting from the unconfined concrete and the section properties. It's another nice tool that basically allows the user to produce this kind of models much faster. And these are just a bunch of the results of the analysis that we have run. Here we have examples of absorbing boundaries. Here we have a soil structure interaction test on definable soil. Here we have a test of a pile on a soil. Here we have modeling of damage and a cyclic analysis of material failure. So we can do quite a lot of things. Now, well, this brief presentation is finished now, so I will start with the tutorial. So if you want to follow the tutorial, and you're already logged in your DesignSafe account, if you go on the data depot under community, I uploaded all the files that we are going to use today. So you can see them, you can work with them under, so community, training, webinar STKO intro, and here you have tutorial 001 fiber column. If you want, you can download it. You have already the input file that we are going to create now, all the TCOL files that have been already generated, and the output file. Okay, so now let's start with the tutorial. So let's go in the workspace. We are here. So the first thing we want to do is to start the STKO to do the preprocessing. So you go under visualization, and here you have STKO. Now you choose a desktop resolution. I choose this one. Maximum job runtime here, okay, let's say 2 hours, but it will be much faster. And then a job name. Here we use tutorial 001. Here I leave the default, so the output file will be located inside this folder. And so I just run it. So you give it a couple of seconds, and the virtual machine with STKO will pop up soon. Okay. Okay, once this window pop up, you just click on connect. Okay, and here now you have your version of STKO. Now in this case, I need to resize, since it doesn't fit the screen, I need to resize the screen so you can see everything. Scaling, okay. So just maximize it. Anyway, okay. Now when STKO opens, let me remove this one. Okay. You are in the preprocessor. Then you can move on the postprocessor using these two tabs. Now we'll start with the preprocessor. So when you're in the preprocessor, the first thing that you want to do is to create your geometry. Now in this example, the geometry will be very easy, so we're going to create just a column. As any CAD, for example, here selected lines, you can either input the location by clicking on the work plane like this, or typing on the input panel like here. For example, now I want to create a 3 meters high column. Let me put 2.5 meters on the Z direction, 2.9 meters, sorry. And then another 10 centimeters, just because, as I will tell you later, I will need to apply an imposed displacement. So I need that the be meant to be elastic. So I need these two views. Okay, so this is our model. Let me just resize the grid because by default it's much smaller. Okay. So this is our model. Now, of course, typically you want to do much more complicated models. So you can start with the curves, then you have tools for creating surfaces, solids, and all the Boolean operations. Now, in this case, we are done just with these two lines. So we have just one geometry, two edges, and three vertices. So they are all connected together. Now there is this tab called interactions. Now, interactions are typically used when you want to model the connections between these joint geometries. But this is not the case, so we don't need them. Probably we'll talk about interaction in future webinars. Now that we have the geometry, we need to start creating all the things that we need for OpenSees. Basically, we start with definitions, which are basically the definition of time series or friction models. Then we will move to physical properties, material and sections, and then the element formulation, boundary condition, and the analysis. Okay, so in this case, what we want to do at the end of the day here is to create an analysis, a first analysis step with a vertical load on top of the beam, and then we will apply an post-displacement cycle on the top. So we need two time series. The first one will be just a ramp. So when you want to create the definition, you either can do it on the work tree, or you can do like here on the ribbon bar, in property, new definition, it's the same. So you can choose a name. The first thing you want to do is a ramp. And here you can choose the model. The model is a time series, and then we choose linear. And we don't need to customize anything. We are fine with the default values. Okay. Now we need a displacement cycle. Let me call it cycle. And let me select a time series of type path. Now for the path, we want to create a displacement path, and now you can go here, you can edit this vector, and you can add as many entries as you want. But in this case, I already have them in a text file, and you have them on your folder that you will be downloading. So I already downloaded here into shared data, and there's a file called cycle. It's a text file, so you can open it with leafpad. So here, accessory leafpad, okay. So select them, Control-C, Control-V, just paste them. That's fine, and we need a DT of 0.1. So this will be our displacement cycle that we impose on top of the column, okay? Now, next step, we are going to create the physical properties. What we want to do now is a fiber-based reinforced concrete column. So what we need, the first thing that we need is a concrete model, a uniaxial concrete model. So let me do a little bit of room here. Okay, so let's create concrete. So optionally, you can give a color. This is not mandatory, but it will be easier for visualization. So just pick a random color for the concrete. And then you choose a model. You go here, we want a material. We want this material to be uniaxial. And we go and find a material model that we like. In this example, we choose concrete 02. Then we put some material parameters. I will go click fast here. Minus zero stress. Then I will show you the effect of these parameters. A nice thing that we have implemented in STKO is that you can now test the material parameters before doing the analysis. So if you are not sure about what this parameter means, you can either go here, for example, you don't know what this parameter is, you go here, you have the description and the link to the online description in the OpenSees website. And then you can test them. Here you can, for example, you can choose one of the strength patterns that you want to apply, like this one, for example. You choose a number of steps. There is a small OpenSees version inside STKO, so you can test them here. But then you will use the OpenSees in DesignSafe to do the Boolean analysis. So let's do this test. You will see the documentation what this parameter mean. I want to go fast. And you say, okay, for me, this behavior is fine. Let's say, okay. So the concrete is fine for me now. I will do the same for steel. So you click here, add a new material. Let's define the steel for the rebars. Once again, I change the color. I'm going to pick a random color. Once again, under material, uniaxial, steel reinforcing steel materials. And let's use our steel 02. Here I will use these parameters. Oops. And the elastic modulus. By the way, in STKO, you don't have the unit system, so you have to be consistent. Now I'm using millimeters and newtons. So let's test also this one, make sure that the parameters are what we expect, and this is fine, okay. So concrete and steel are already defined. Now we need the fiber cross-section. So you can go here. Now fiber cross-section in STKO can be defined in two ways. The general one, or let me call it fiber. So the general one, well, of course, is under section. The general one is fiber. But when you choose fiber, you have to click here, and then a new window will pop up where you can draw the cross-section by hand. Now, this is the most general way, but it's a little bit tedious every time you have to do a rectangular cross-section, because that is a typical section you don't want to draw every time. So when you have to do something which is not standard, like not rectangular, you can go here. But in this case, we want a rectangular cross-section, so we have an easier tool, which is the rectangular fiber section. Okay, so we go here. The parameters are pretty well described, so I will put a random value for the torsional stiffness. We don't need it. And we will make 300 millimeters times 500 millimeters. And then let me just change the properties of the reinforcing steel. So this is the diameter of the corner, of top rebars, left rebars, and so on. And on the left, you can see the image of the cross-section that is updating. Okay. Now the geometry is fine. Now we go here and we can choose the material models. And in this case, we have a nice feature because, as I told you before, you can just select the concrete model for the cover. And if you don't select anything for the core, this tool will automatically compute the confined concrete based on the stirrups data. Now, this is not the main topic of this tutorial, so we'll start with the standard, with the same concrete both for the core and for the cover. And then we will choose the rebar material. Okay. And this is fine. Okay, that's fine. Okay. So the cross-section is done. Now, as I told you before, we need an elastic section for this small piece up here. Why? Just because we're going to apply an imposed displacement, and imposing an imposed displacement on a material which has softening directly is not a good idea. So let me just create the same cross-section but linear. Elastic section. We go here, section, elastic. Is much easier to define. You go here, you choose into a database. This is we want a box, and we want it to be 500 times 300. Okay, and we pick up the Young modulus of concrete, the same that we've given before. Okay, the elastic section is here. And now let me create one more thing that we need for beams, which is the beam property. Why? Because for beam, we don't need only to assign a material, but we also have to define the integration rule. So we need one beam property for the linear element. Okay, let's go here, special purpose, beam column, beam section property. Here you can choose among all the types of integration rule that you have in OpenSees. Now, in this example, we choose the standard integration rule, just 5 integration points, doesn't matter. And here we choose the elastic section. And let's give it a color, so we will see if everything is properly assigned in the preprocessor window. Okay. And then let me create another one. Let me clone it because it will be the same, but with the fiber cross section. So it will be used for the nonlinear part of the model. Which is the same, but just we change the section tag, which is the fiber one. Okay, let me change the model color so we can see it. Let's pick a random one. That's fine. Now we created all the property that we need. Now we can assign them. Now we want to assign not the entire geometry, but only to subshapes. So we switch off this button here so we can select only subshapes one at a time. So this one will be nonlinear, so just drag and drop it. And this other piece here will be linear, so we drag and drop the linear property. Okay, that's why we assign colors, so we can double check if everything has been assigned correctly. Now that we have the physical property, we can go ahead and create element properties. But first, let me save the model because I've done this, but I've never saved it. Okay, so let's create a new folder here. And it will be tutorial. I call it 002, but it's the same as 001. Okay, and you save it. Perfect. Now we go ahead with the element property. Now in this case, we need the same element formulation for the entire model, which will be a displacement-based beam column element. So we go here, we choose beam column elements. As you can see, we have all the elements that are in OpenSees. We go beam column elements, and we choose displacement beam column. We are doing a 3D model, so we choose the three-dimensional dimension, and we are fine with the linear kinematics. And okay, so we just select the entire geometry, and we drag and drop the element property. Okay. Now the next step are conditions. So you can go here, or we can work in the work tree. It's the same. So the first thing that we want to do is to create a fixity at the base. Now keep in mind that we are going to create all the condition, all the boundary condition, but at this point they will be just defined. They will not be inserted into the analysis. So the order in which you create them is not important. It will be important instead the order in which you put them in the analysis step later on. So let's first create a fixity at the bottom node. Some more room here. And let's call it fix base. We can choose among these types. Now we want a constraint. Here you can choose between single point constraint or multi-point constraints. Here we want a single point constraint and the fixed command that you have in OpenSees. Here, once again, you have to choose both the dimension and the model type. Now we are working in 3D, and we're working with a DOF set made of displacement and rotation degrees of freedom. So you can choose UR, displacement plus rotation. If you're doing soil modeling, probably you need the displacement pressure, or if you're doing just mechanical solid modeling, just the displacement. In this case, we need displacement and rotation, and we want to fix everything. So we click on all the options. Then, before closing the window, we select the targets that will be that will have this condition. Now, in this case, just the bottom node. So press OK, and here you have this condition. Now, the next one, we want a vertical load on top. So once again, new condition, add. Let's call it vLoad. Go on model. Now we go on load. This is going to be a concentrated force, so we go on force, and we have here node force. Now there are many options. I'm not going to explain all of them. Here we choose constant, because otherwise we can make a force as a function of spatial coordinates, but this is not important now. So it will be constant along the z direction of minus 500 kilonewtons. Okay. Once again, select the node that will take this condition. Here it is, and then OK. Now you have the vertical load here, and then we are going to apply on the same node an imposed displacement. So once again, add. We call it push. We go here, load, single point constraint, single SP, which is the prescribed nodal value. And similar to the fixity, here we have to define the dimension and the offset UR. Now there are a few other options that are not important now. We're going to push it just in the X direction of a quantity like 120 millimeters. And once again, we select the target node. Let's put it back, press OK. Okay, now we are done with the definition of the boundary condition. Let me save the model once again. And now the most important part, we are going to define the analysis steps. Basically, the order in which you put things here will be the order that you will see in the TCOL file. This is very much important. So typically, the first thing that I do is to create the recorder. So I go here, first analysis step. Let me create some more room here. So the first thing is the recorder. So you go under model, you choose recorders. Now we have just one. As I told you, we do not support the text-based standard recorder of OpenSees, but you can still add them. Why? Because STKO only visualizes its own database, so the NPCO recorder. Now here you have a lot of options. Let me just collapse them, and I will show you one by one. Okay, so the first thing that you want to do is to give a name. Now, the name will be the name of the file that is going to be created. You can either click here and choose the folder using the file dialog. But remember that in this case, the file will be an absolute path. So if you pass this model to your colleague probably is not going to find the same path. So the other option that I typically use is that I just type a name, like example 002. And then it will be created inside the same folder where the TCOL files are. So it will be, in this case, a relative path. Then you can choose the nodal results that you want. In this case, we just want displacement, rotation, reaction force, and reaction moments. And then you have all these other things. Then we are going to choose the element results. And we want section, force, and deformation to visualize forces and deformation at the Gauss point level of the beam. And we also want to record stresses and strains at each fiber. If for some reason you need other results that are not mentioned here, you can create your own custom results here. So you go here, you make room for all the results that you want. Let's say you want to store a result that is called damage. You just write the word here. Now this is not the case in this example. So we are fine with them. Then you have a few other options. The time option, the default one, here you have the record frequency. So how many times the recorder should record the time steps. Now the default is always. So every time a time step converges, it will be recorded into the output database. Otherwise, if you want to limit the size of the database, you can choose, for example, to say every increment of time or every number of time steps. Now, in this case, we will record every delta, every time increment of 1 to the minus 3. Then you have a few other options. For example, if you want to record results only on parts of the model, you can choose regions, but this is not the case. So we are fine now. Now, the next step is to apply the boundary condition that we defined before. So the first step, let's call it add constraints. We go here, patterns, add pattern, constraint pattern. And here you can choose as many single point constraints and as many multi-point constraints that you want. Now in this model, we just have one single point constraint. So we make room for this one here and we choose fixed base. So the first thing that we do is to apply a fix at the base. Okay. Now we apply the vertical load. So it's very similar to the constraint pattern. So let's call it add vertical load. We go here, pattern, add pattern. Well, a pattern can also be removed if you want. Add pattern, load pattern. Now in this case, you need some more options. First, you need the time series. Well, the vertical load will be applied with a linear ramp. And then you go over here because it's a nodal force. You make room just for one, and you apply the vertical load. That's fine. Now at this point, we want to do the first analysis. The first analysis would be just a static gravity analysis. So we go over here, we go on analysis command, and we choose static. We go on transformation method for the constraints. Now, since we are going to work in parallel with OpenSees and P, let me make some more room here. We choose the number, which is the parallel one. Otherwise, it will not work. Same thing for solver. You need the mumps or the parallel profile, but in this case, we choose the mumps, which is the general one. Then we are going to choose, in this case, Newton with line search. And we are going to choose here as the test command non-displacement increment test, in 1 to the -7 for the convergence and 20 iteration. And for the vertical analysis, we also want to visualize how the model converges. So you can choose the flag here. Then it will be a load control, and I'm fine with 10 increments with 0.1 increment each one. So the total time will be 1. After this, we want to apply, we want to keep the load constants, and we want to reset the time to 0. Okay. Now we can start applying the displacement cycle. So once again, this is a load pattern. So add horizontal load, pattern, add pattern, load pattern pretty much as the previous one. Now we choose a different time series, which is the cycle. And then we are going to put the post displacement here because it is a single point constraint. And let's put it here to push. Okay. And finally, we need the final analysis. We can just clone it because we will change just a few parameters. Clone, edit, and we call it analysis 2. Okay, it will be the same. Let me just go ahead, let me do some modification. First, I don't want to print the convergency, and I will show you why. Then we will do a load control, but I will do 0 increments. I will explain you why, because here I need very small increments for the convergence of this problem, but we are going to use a custom adaptive time step. So I will show you another feature that we have in STKO, which is the ability of creating custom TCL scripts inside STKO. So here I just need to define everything, but I will not start any analysis just by putting 0 here, okay? Now let's say for some reason you want to do something non-standard, something that is not available in STKO. Like in this case, we don't have the adaptive time stepping. Then you can use your own script, because many times people ask us, okay, but if I want to modify the TCL file, how can I do it? You can do it directly inside STKO. So here, for example, I create a new analysis step, which is a NIST command, custom command. A custom command is basically a TCL script. So you can directly write your TCL file here, and the TCL file that you put here will be written directly at the right location. Now in this case, once again, in this folder that you can download, there is the code for the adaptive time step control. So you can open it with the text file and copy paste everything. So Control C and paste it. So basically now it is not important what this code is doing, but it's just doing a adaptive time stepping based on the convergence property of the problem. And then it will print the convergence in a nice fashion. Instead of writing all the iteration on all the processor, it will write the percentage of the analysis. This is just an example to show you that you can do whatever you want with the custom commands. And let's call it adaptive. And press OK.
Hey, Massimo, I'd like to interrupt just briefly because I forgot to mention at the beginning when I introduced you that if the people watching have questions, please type them into the chat window, which you can find kind of in the bottom ribbon
Yes.
of the Zoom meeting. And then we'll leave some time, maybe 5 or 10 minutes at the end to answer those questions. Okay, perfect. Now I'm done with the model, so we'll start very quickly how to run the analysis and then visualizing the results. So we have, let's say, 5 minutes for questions. So let's save everything. The last thing that we need to do is to do the mesh. Now, as you may know, in this example, you don't need
to do a mesh, but since we are going to use a parallel solver, we need some more elements. So here I'm going to create a mesh with a uniform size of, let's say, 150 millimeters, just to have some elements. Once you have assigned the global seed, you just build the mesh, and you're fine. Now, if I want to create a model for parallel analysis, I'm going to partition the model. Now, this model is quite small, so let's say 4 partitions are enough. Let's call partition. Here you can see all the partition, you can debug them, and that's fine. Okay, done. I'm fine with this partitioning. I save everything. And then I go to analysis here. Don't run the analysis because we don't want to run it with the OpenSees that is inside STKO because it is just as much OpenSees. So we just write the input file. And we choose a location, like in my case, tutorial number 2. Okay, I create a new folder called input. And I'm going to create all the input file right here. Okay, now everything has been correctly written. Let me just show you where they are very quickly. My data, tutorial number 2, input. So you have all the TCL files here. Now, if you are curious, you can go there and see what's going on there. That's fine. Now, we can go once again on our workspace, and now we're going to run the analysis. So you go under simulation, OpenSees. Now, be aware that you have to choose the OpenSees MP with the STKO label here. Otherwise, the recorder will not work. So you choose this. You choose the input file. Now we have, let me just update it, otherwise I don't see the new folder that I created. Just a second. Okay, now I have tutorial number 2. Okay, so let me just select once again OpenSees and P for STKO. Let's go here on tutorial. The input directory will be this one. So you just drag and drop it here. The TCL file is the main.tcl, that's fine. So you choose uptime, but it will take just a minute. A job name, I typically call it like the same one as I call the preprocessor, but with a run. But it's just a naming convention. Now be aware that if in STKO I've chosen 4 partitions, I need to use a total number of cores, which is 4. So in this case, just 1 node and 4 cores. And you can just click run. Now, basically, the analysis will take just 40 seconds, but it will take something more for the analysis to complete here. So I can just go here and I show you the results very quickly. And then I will show you where to go and take those results, because now they are already been generated. So when the analysis is done, you go here under Open Database, and you go and find them. Now, typically, those files will be under my data, archive, and then the name of the job that you give. Now, in this case, because we don't want to wait for it to finish, I already have the output, which is the same output that you can visualize there. I have it, where do I have it? Archive, jobs. The jobs that I've run before was this one, I think. Yes. So as you can see now, you have many output files, one for each processor. But fortunately, in STKO, you just select one, and STKO will recognize that they are part of our partition database. So it will open them as if they were a single file. So the next thing that you do is to create a new plot group, and then you can choose one of the plots. So the typical one is the surface plot. The surface plot is just the standard color surface here. And you can see results such as, let me move this one, such as the displacement, section forces and deformation. Let me give some more room here. Okay, so you can choose the results, the components, and so on. And here you have properties for the video. Or you can do another plot group, and I will show you just the basic plots that we need. For example, the Gauss plot, something nice if you want to visualize. Let me get rid of the grid, I don't need it. For example, if you want to visualize results on the directly on the integration point, so without any interpolation or extrapolation to the nodes. So you see the results actually on the Gauss point. For example, I want to see section moments. okay, like this. Or you can see fiber results. So I create a new group and I choose beam shell fiber color map. And in this case, I can choose among the other results that are compatible with this plot, which is the section fiber strain or stress. Okay, now in this case, we have just one component. Now, when you see the stress, typically when you have reinforced concrete, you just see the values for the steel, so you can switch on and off one of the materials. So now you see only the concrete here, for example. Now let me increase the deformation scale. I will show you just a small video. Here you have the tools for the video. You can run it, or you can just move the slider bar here up and down, whatever you want. So you can see how the stress is moving on your element. And then, of course, you, instead of just visualizing the results like this, you can actually also extract results, for example, to create charts. Now, if I want to create a plot of a force displacement of the load displacement curve of this model, so let me go here and let me see, okay, I want to extract data from nodes. So I go here, extract data, and I choose okay on nodes because I want to extract force and reactions. And I want to extract them only on the second stage of the analysis, which is the horizontal analysis. And then I choose displacement versus reaction force. Now I've assigned an imposed displacement here. So at the same node, I have both the displacement and the reaction force. Next, you choose the node. I've already chosen one. And then you choose a name. For me, a new chart is fine. Okay, and this one will be the output. And you have the data here, so you can copy paste it. Let me select it. You can copy paste it and on your Excel spreadsheet, or you can just visualize it here. You can do the same thing for Gauss points if you want to output moment curvature, or you can do the same thing on fibers. For example, let me show you the behavior of one of the concrete fiber at the bottom. Let me go here. Let me select one. Oh, too much. Let me select one concrete fiber, and once again, extract data. In this case, I want data on sub-integration point, which are fibers. Once again, from the second stage, strain versus stress. And you have the output of your fiber. And so you can do many more things, but now I think for the tutorial of today, it is fine enough. Here, I just wanted to show you the entire workflow, but I think all the other nice features like the Python interface, how you can program the Python interface, how you can do more complicated models, modeling contacts, interaction, and so on. We will do them in dedicated webinars in the future. So now, if you have any questions, please, we have, I think, other 10 or 5 minutes, 10 minutes.
Yeah, we have between 5 and 10 minutes. So I'll clap. Good job. I think everybody else is muted, but they're all clapping too.
Thank you.
Okay, we do have one question that's come in from Elok Bata. For nonlinear dynamic analysis for stone mortar, can you briefly lay out the steps from start to finish? And can we have access to similar codes already written in OpenSees?
Yeah, I mean, stone mortar.
Yeah, for stone mortar.
You mean stone masonry and then the mortar between?
I think, yeah, it just says stone mortar, but I think for stone masonry with the mortar between the stones, yeah.
Yeah, because I don't see the question. I do see the question here because I don't see it.
Yeah, if you click on the chat on the bottom, you'll see it'll open up a pop-up window that'll have questions in it.
Okay. Well, I don't see any here, but anyway, okay, here. 5 more. Yeah, no chat here. Okay. Yeah, so for nonlinear and stone mortar, you can do basically the steps are pretty much similar to this one. You need to do either a surface model or a solid model, depending on how you want to model this stone masonry. And then how you want to model the mortar. For example, I've shown you before some example for regular masonry. Let me move to this one, this thing here. This one has been done in STKO and OpenSees. In this case, I model the mortar as a continuum element because we have our own constitutive model for concrete and masonry. Otherwise, you can use one of the zero-length material models that are in OpenSees. And through STKO, you can model those zero-length elements as distributed cohesive zones. Unfortunately, in this case, you don't have the interaction between the shear and normal stresses. So you have to do your own code. But anyway, the modeling is a little bit different because instead of modeling just lines as I did before, you need to do surface model if you want to do a planar analysis, or solid modeling if you want to do an entire solid model. Then I have another question there. Can this tool be used with models that have not been created in STKO? Yes, of course, but only partially. Because as I told you, STKO and OpenSees are separated. If you create your model by hand, like you have done up until now, you just need to input the MPCO command on the TCOL file, and I will show you how. Let me go here. Let me go here. Let me open the TCOL file created by STKO. So imagine now that these TCOL files have been written by you by hand. In the analysis step here, I have this command, which is the MPCO recorder command. So if you have OpenSees with a version equal to or higher than 3, you can just input this command, and you will be able to see. And you will be able to see the results on the STKO postprocessor without creating the model in the STKO preprocessor. Okay. Can we upload existing TCOL files to STKO preprocessor and then overwrite recorders? Of course you can. I mean, you upload the TCOL file, then you write this command here for the recorder, and then you run the analysis. Yes, you can. And you will see the results.
I have a question too. As new material models or elements are introduced into OpenSees, do you update STKO to incorporate those?
Yeah, we do it if they are on the repository. But if you have, for example, your own version of OpenSees and you don't put that model on the repository, of course you have to do it by yourself, and you can, because the interface between STKO and OpenSees is in Python and is customizable by the user. So of course you can do it. And they are pretty easy. Let me see if I can show you how they look like. So for people interested in how to customize STKO, I will show you. Now here, the installation, I think, is here, STKO install. So whenever you have your installation folder now here, or, well, I think you cannot customize it here on the DesignSafe-CI machine, but if you have your own STKO in your local computer, you can do it. You have external solvers, a folder called external solvers, full of Python files. Like in this case, for example, if you add a new material model, you go into physical properties, you go into materials. Let's say you created a new ND material. Like for example, this one, damaged TC3D, is a material model that we implemented, but it's not inside the standard OpenSees. And it's just a Python file. Well, you need to know Python. You need to know the interface between Python and STKO. But it's just a matter of writing a few functions to, for example, to give a description of the parameters, to give the name of the parameters. For example, I want to say this parameter should be a scalar with a certain dimension and should have this, this description. And then you need another function that tells basically STKO how to write this model into the TCOL file. So you basically get the parameter back and you write the TCOL string here. So yes, if you have your own model, we can either do it if you put on the global repository so it is visible to us, or you can do it by yourself if you keep it proprietary.
Then there are two more questions, and then I think I'll have to close it out. So let's answer the last question first. Is it possible to model confined masonry structures?
You can do it. I think you need to do the 3D, of course, in this case. Otherwise, you will not capture the confined behavior, but you can do it. Of course, you need your own material model. Soon we will upload our own material model, which is very useful for masonry, which is both in 2D and 3D. and uses a particular integration algorithm which is called Implex. So it is also very robust because it is a mixed implicit explicit model, and it will be online soon. And then I don't know if there are other models that can be used in OpenSees. Probably there is a concrete model that you can use for measuring, but I'm not completely sure about that.
And then are there any example videos for STKO?
Yes, of course. Now the documentation is basically, if you go on the website, let me show you. We have both the documentation, so you go on AsdeaSoft, and you go under support. You have manuals, tutorials. Oh, let me move this one. But you have an introduction STKO, the installation manual, the reference manual, tutorials, video tutorials that are here or on our YouTube channel. And then you have document tutorials, and then you have a forum. So you can go into the forum, you can post your question here, and we will try to answer as soon as possible. So we have quite a lot of documentation, and we are trying to increase it.
Great, thank you. So I think I'll take back the screen just to show a few slides as we close out. But thanks again, Massimo, for this great presentation.
Can you answer Leon's questions, please? Which is this one, okay.
The one you just answered, yeah. So I think we got it. And
Yeah.
Can you click the share button again so that I can take back the share?
Yes.
Thank you. Perfect. Okay, and then I should mention that the webinar that you just saw has also been recorded along with all of the other DesignSafe webinars, and you can find them through the DesignSafe website here at the Learning Center under training. So you'll be able to follow along with his answers to all of those questions and the full presentation.
One side note, sorry, I forgot to mention the researcher that helped us in developing some of the Python scripts, which is Diego Talledo, which is following us right now. So thank you, Diego. Okay, thank you.
All right, thanks. And then we'd just like to thank Massimo and the DesignSafe crew here, and feel free to contact us if you have any questions. You can find us on Slack to ask questions that way, email, or there's also support tickets. So thanks for joining us in today's webinar, and thanks again, Massimo, for the nice presentation.
Thank you.